The goal of this video is to present Euclid's proof of the theorem of Pythagoras. Simplified. I hope that it will be understandable by any interested high school student. The four-sided figure ABCD is a rectangle. All four angles are equal right angles. The opposite sides are equal. The opposite sides are parallel. The four-sided figure EBCF is a parallelogram. It has no right angles. Nonetheless, opposite sides are equal and opposite sides are parallel. The four-sided figure ABGD is called a trapezium by Euclid. There is another one, EGCF. These two trapezia are different from each other. The side AB in the left one is not equal to any of the four sides in the right one. But the side AD in the left one is equal to the side EF in the right one because both segments are equal to the segment BC. But the two trapezia are related to each other because they are equal in area. This fact results when we look at the proof of Euclid's theorem 35. Note that when Euclid says two figures are equal, he means equal in area. Theorem 35. If a rectangle and a parallelogram are on the same base and in the same parallels, then they are equal. Here's the proof. In the figure, the rectangle ABCD and the parallelogram EBCF are on the same base BC and in the same parallels AF and BC. The triangles ABE and DCF are equal because all three sides are equal. The side AB in the left triangle equals the corresponding side DC in the right one because they are opposite sides of the rectangle. The side BE in the left triangle equals the corresponding side CF in the right triangle because they are opposite sides of the parallelogram. Now for the third sides A, E, and DF. The third side AE is the segment AD extended by the segment DE, and the side DF is the segment EF extended also by the segment DE. The two sides are thus equal segments AD and EF extended by the same segment DE, so that the whole sides must therefore be equal. So the third sides of the two triangles are also equal. Notice next the triangle DGE. It is common to the two equal triangles. So, if we remove it from each, then the remaining trapezia figures must be equal. Now look at the triangle GBC. If we add this triangle to each of the equal trapezia, then the resulting figures, namely the rectangle and the parallelogram, must be equal. This concludes the proof of Theorem 35. Now we will look at Euclid's Theorem 41 because it is used in 4 places in the proof of the Pythagorean theorem. It follows easily from Theorem 35. Theorem 41. If a rectangle and a triangle are on the same base and in the same parallels, then the rectangle is double the triangle. Construct the segment BH equal and parallel to the segment CF so that we have a parallelogram HBCF and a rectangle ABCD on the same base and in the same parallels as in Theorem 35. The segment BF is a diagonal of the parallelogram, and the diagonal of a parallelogram bisects it because the two resulting triangles agree on all 3 sides. Thus, the parallelogram and hence the rectangle is double the triangle. This completes the proof of Theorem 41. Now, here is Euclid's proof of the Theorem of Pythagoras. We start with a right triangle ABC with right angle at vertex A. The segment AB is the short leg and the segment AC is the long leg. The segment BC opposite the right angle is the hypotenuse. Construct squares on all 3 sides. The first step in the proof is to construct a line segment from the vertex A perpendicular to the hypotenuse and extend it to the point L. Euclid's plan can now be seen. The square on the hypotenuse has been divided into 2 rectangles, and they will be seen to be equal in turn to the squares on the legs. Next, draw in the segment AD. Compare the rectangle BL with the triangle ABD. They are on the same base BD and in the same parallels, so the rectangle is double the triangle. Now, draw in the segment FC. Compare the triangle FBC and the square on the short leg. They are on the same base FB and in the same parallels, thus the square is double the triangle. But the 2 triangles, ABD and FBC are equal. They agree side, angle, side. The side AB equals the side FB. The side BD equals the side BC. The angle ABD is the angle B in the triangle ABC plus a right angle, as is the angle FBC. Thus, the square on the short leg and the rectangle BL are equal because both are double equal triangles. The rectangle CL is likewise seen equal to the square on the long leg by drawing in the segments AE and BK. This completes Euclid's proof.